Hopefully we're live. All right. That sounds okay. Yesterday morning, the audio was super bad. It sounded I was listening back to some of it, super robot-y, kind of clipped. So hopefully whatever that was, it's not a problem anymore. Fingers crossed. And I will warn you right now that I have been having a lot of network instability this morning already. So hopefully, I'm not going to disconnect randomly, but if I do, that's why. Hi, welcome to the Rasa reading group. It is, you will have noticed, just me today. We have, so this is actually one of a pair of anyway, it's basically a company holiday, but we're staggering it, so I'm going to be out next Thursday and Friday, and a lot of people are out this Thursday and Friday, so it's just me. Welcome to the reading group. I'm going to have a little coffee, and then introduce the paper. So, those of you who have been watching the channel for a while or have watched my other stuff know that I am all about small, efficient models. I'm not especially enthused or delighted when someone's like, we used more compute and more weights, and wow, our model did better, which is like, yes, fine, I guess. I don't think that's especially interesting, and it's not necessarily... Just because a model has really good performance on a specific benchmark doesn't mean that I'm necessarily going to want to deploy it in my projects, especially if it's enormous and expensive, which is why I was so excited about this paper. So this paper is Reformer, the Efficient Transformer, and this is actually the copy that went under review for ICLR, the International Conference on Learning Representations 2019. I'm pretty sure it got published in 2019. I could be wrong about that. Blind submission. So submitted September 2019, modified March 2020. Okay, I'm like 80% sure that this paper was published in ICLR 2019, and I'm just going to real quickly check that because now I'm doubting myself. But the researchers are all out of Google. And the code for this paper, let me zoom in a little bit. The code for this paper, can I move to the side? Nope. Is already on GitHub. So if you're interested in checking that out, it's in this repository that is linked here. An open review, if you're not familiar, a lot of sort of, I'm just going to move myself. Whee! A lot of sort of machine learning conferences that are not ACL conferences use open review as a way for doing their reviews. So basically you upload an anonymous paper and then the reviewers leave their reviews, and the reviews are public. So you can see that the paper was accepted. Oh, it was ICLR 2020. Well, I'm going to have to go tweet a correction to the tweet that I did. I guess it was submitted in 2019, and that's where I got that number from. So you can see the reviews and then the author's responses, and it's all open. ICML is like this, ICLR is like this. It's a really nice reviewing platform. And if you are, especially if you're newer to the field, I would see if you can find a paper on open review before you look to archive, because archive is a preprint service, right? And sort of the idea with preprint services is that it's a way to share papers to other people in your community before they've undergone peer review. And kind of baked into the model is the assumption that you, the reader, would be capable of doing peer review on those papers, which is true for a lot of people who use archive, but also not true for a lot of people who are using archive as sort of like a reference for work that they may or may not have the sufficient background to evaluate in context. So I know I say a lot of stuff about archive. I don't think it's a bad idea. I don't dislike archive, but it's good to be aware that the papers there are of much more variable quality than you would see at something like a top-tier conference like ICLR. So that's the historical background on the paper. Hello, Enrique says melting near Madrid. and Lucas, one of the authors, was yesterday in Break into NLP Deep Learning AI Course 3 launch. Oh, fun. I don't think I've met any of these authors. I could be wrong about that, but I don't believe I have. All right, let's jump in. So obviously the authors aren't listed here because this is the anonymous version. I'm going to move myself back onto my custom side. That's not too bad. Okay. Reformer, the efficient transformer. Abstract. Large transformer models routinely achieve state-of-the-art results on a number of tasks, true, but training these models can be prohibitively costly, very true. I think the estimates I saw for GPT-3 were in the realm of $12 million just on compute, especially on long sequences. We introduced two techniques to improve the efficiency of transformers. For one, we replaced dot product attention by one that uses locality-sensitive hashing, changing its complexity from OL squared to O of L, where L is the length of the sequence. Furthermore, we use reversible residual layers instead of the standard residuals, which allows storing activations only once in the training process instead of n times, where n is the number of layers. The resulting model, the reformer, performs on par with transformer models while being much more memory efficient and much faster on long sequences. So the things that make transformers exciting and useful as a sort of family of architectures, you don't have that training bottleneck that you do with recurrent neural networks where you have to finish each time step in series. So you can ignore, you don't have to step through a sequence. You're looking at the sequence all at once. And then the other benefit is that they can handle long distance relationships a little bit better than most RNNs. So RNNs tend to prioritize things that are closer to the current point that you are in the sequence, which is honestly kind of more like the way that language processing works, certainly on like a syntactic level. But transformers allow you to, at any point in time, put attention on any other time point in your larger input sequence. So they are a very useful family of models. We use them in Rasa. So in particular, for dialogue management, we have the TED policy, which is based on Convert. Is the TED policy separate from Convert? I'm not going to commit to that statement. I think I might have confused my acronyms. But anyway, we do use transformers quite a bit in Rasa, especially for picking what to say next with your assistant. But again, they slow. They're really slow. They're really big. And this provides some ways of making them smaller. And probably we're going to see all of that stuff again right here in the introduction. The transformer architecture, Vaswani et al. 2017, is widely used in natural language processing and yields state-of-the-art results on a number of tasks. To obtain these results, researchers have resorted to training ever larger transformer models. The number of parameter exceeds 500 million per layer in the largest configuration reported, Shazier et al. 2018. They are much bigger now. Well, the number of layers goes up to 64, Alfu et al. 2018. T5, GPT-3, both much bigger than those. Transformer models are also used in increasingly long sequences, up to 11,000 tokens of text in a single example produced in Liu et al. 2018. And when processing other modalities like music and images, even longer sequences are commonplace. Okay, so it looks like maybe this introduction was written like a little while ago, because it's not talking about some of the bleeding edge research from where I'm standing right now in July of 2020. But good sort of summary of where the field is right now. These large-scale, long-sequence models yield great results, but strain resources to the point where some argue that this trend is breaking parts of NLP research. Oh. Hacking semantics leaderboards. Interesting. I'm not familiar with this. Actually, let's go check it out. Anna Rogers! You may be familiar with Anna Rogers from our L3AI event where she was on a panel with Emily Bender and some other researchers that I meant to be on, but I had laryngitis and I couldn't talk. And also she wrote the paper that we read, the first paper we read in the reading group about Bertology. So talking about some of the problems with leaderboards in NLP. Yeah, and it looks like she's summarizing, yes, this is absolutely my biggest gripe with a lot of the transformer research today. More data and compute equals state of the art is not research news. 100% agree. Where I think this paper, which we haven't finished yet, I think is more interesting because it provides some approaches for making the paper small, making the models small, actually. Raj says, do you have any beginner-friendly paper reading streams or playlist? One where someone doesn't feel so overwhelmed as to what is happening. I mean, hopefully this. Please feel free to ask any questions you have in the chat. The fact of research papers is that they are written for a researcher audience, which means that they are written with the assumption that you are already in the field, understand the basics, and are interested in what people are doing that is new and advancing the previous work. So there's sort of this built-in assumption that you are familiar with the previous work, which is why I'm trying to like contextualize this as much as possible for y'all. And hopefully this should be beginner friendly. Please feel free to ask any questions. And if I don't know the answer, we can look it up together. But yes, just I have a bigger model is not very interesting research in both Anna Rogers and my opinions. Blah, 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 blah. Many large transformer models can only realistically be trained in large industrial research laboratories, and such models trained with model parallelism cannot even be fine-tuned on a single GPU, as their memory requirements demand multi-accelerator hardware setup, even for a single training step. So the original BERT model, if you'll remember that, sort of like the big contribution that the authors argued for was that you had this large transferable model, and then you do a little bit of transfer learning on top of it. And if you cannot fit it in memory, you're not gonna be able to update your weights, right? Do large transformer models fundamentally require such huge resources, or are they simply inefficient? Consider the following calculation. A 500 million parameters used in the largest reported transformer layer account for 2 gigabytes of memory. Activations for 64K tokens with embedding size 1024 and batch size 8 account for 64K times 1K times 8, 0.5 billion floats, requiring another 2 gigs of memory. If our memory use was only per layer, then we should fairly easily fit a large transformer even on sequences of length 64K on a single accelerator. Further, the whole corpus used to train BERT only requires 17 gigabytes to store. Why is it then that we cannot even fine-tune these models on single machines? So the parameters, I believe, are the attention, and then the activations are the activation function threshold for each of the, these guys in the, oh, wow, Jesus. My mind is blank. Neurons, wow. Wowee. That took a minute. So what they're saying is that you have your parameters, you have your activations, and this is per layer, and there's obviously many, many layers in a large transformer. So you should be able to fit a model in, just if you're looking at the parameters and the activations, you should be able to fit a model on a fairly modestly sized GPU. Ragav says, can you explain what is the transformer architecture? Is it the encoder-decoder pattern? So the Vaswani paper did use an encoder-decoder pattern. So basically an encoder is text to numbers, and then a decoder is numbers to text, if you're working in a text-based format. And a lot of the extensions of it have used the just the encoder. So BERT uses just the encoder to take in text and then create sort of a numeric representation that you can use as an input to another system. And the big thing about transformers is that for each point in your sequence, you have attention to every other point in your sequence and self-attention. And then you have multiple heads that are doing that. So you have multiple copies of the attention with different weights in each of the heads. And then you have like many stacks of this. So that's the sort of general idea of a transformer architecture. We have an NLP for developers video on it on the Rasa channel, which is pretty high level, and then Vincent has a attention series. I think it's 3 videos in his algorithm whiteboard that goes into more detail if you're interested in sort of the nitty gritty. So, and Enrique says there's a pretty good Rasa video explaining it for Diet. Yes, Diet also talks about it. So, why are transformer models so big, where if you just look at the number of, I live kind of near okay, well, hopefully not relevant to me. So if you're just storing the parameters and the activations, then you shouldn't need that much memory. Why do you need so much memory? The above estimate includes only per layer memory and input activations cost and does not take into account the following major sources of memory use in the transformer. Memory in a model with n layers is n times larger than in a single layer model due to the fact that activations need to be stored for backpropagation. Since the depth DFF of intermediate feed-forward layers is often much larger than the depth D model of attention activations, it accounts for a large fraction of the memory use. Okay, so point 1 makes a lot of sense to me. If each layer has separate activations, you need to store them, because when you so the way you train neural networks is you have all these activations, you have data that you send up through the neural network, it gives your prediction, whatever it is that you're looking at, and then using gradient descent, you update the activation layers going back down through your model. So you sort of like information through, get your output, whatever that is. If it's good, you sort of do more like what you just did. If it's bad, you do less like what you just did. Very simple explanation of gradient descent, and then you use that to change what the weights are in your model. And then the second bullet point, since the depth DFF of intermediate feed-forward layers is often much larger than the depth of D-model attention activations, it accounts for a large fraction of memory use. Okay, so in Vaswani's transformer architecture, there is the sort of multi-headed self-attention that I mentioned, where you have attention going to all the other sequence, and then you have just sort of like a plane, I guess, feed-forward neural network in between each of those sort of clumps. It's sort of like a layer cake with jam in between the layers, where the jam is the feed-forward network. So it sounds like those are actually accounting for much more memory than I would have assumed, for sure. And then point 3, attention on sequences of length L is OL squared in both computational and memory complexity. So even for a single sequence of 64K tokens can exhaust accelerator memory. So remember how I mentioned that each item, you have attention to every other item. If you have, in a sequence, so a sequence is paying attention to itself. So if you have a sequence of 4, you need 16 cells to store the attention. If you have a sequence of 5, you need 25 cells to store the attention, because you need to know each pairwise relationship. There's been some work on sort of taking that square and cutting it in half along the diagonal and making it symmetrical, but it is not by default, I don't believe. So these are places where the model get big. All right, we introduced the reformer model, which solved these problems using the following techniques. A, reversible layers, first introduced in Gomez et al. 2017, enable storing only a single copy of activations in the whole model so the n factors disappears. So all layers share the same activations, question mark? Splitting activations inside feed-forward layers and processing them in chunks removes the DFF factor and saves memory inside feed-forward layers. Splitting activations inside feed-forward layers and processing them in chunks. Presumably we're going to learn more about that. I don't know what DFF refers to. Presumably this is sort of fairly standard notation. I guess we'll find out. And then 3, approximate attention computation based on locality-sensitive hashing replaces the OL squared factor in attention layers with OL, and so allows operating on long sequences. All right, I also am not 100% sure what that means, but that's what the paper's for. Okay. I'm just gonna move myself over a little bit so I can gesticulate. We study these techniques and show that they have negligible impact on the training process compared to the standard transformer. Splitting activations, in fact, only affects the implementation. It is numerically identical to the layers used in the transformer. What? That is wild. Okay, so what they're saying is that these things that make the model more memory and compute efficient to train don't change the model. Like, it's just how you update things that's being changed, and you end up with the same model, just trained more efficiently. That is buck wild. All right. Applying reversible residuals instead of the standard one does change the model, but has a, okay, I see what they're saying. So the second one, splitting activations, which I'm still not 100% sure what that means. We'll find out, I guess. That one doesn't change the model. Okay. And then applying reversible residuals instead of the standard ones does change the model, but has a negligible effect on training in all configurations we experimented with. So that's the first bit. Oh, they're changing the order halfway through the paper. Finally, locality-sensitive hashing, this third one, in attention is a more major change that can influence the training dynamics depending on the number of concurrent hashes used. We study this parameter and find a value which is both efficient to use and yields results very close to full attention. Okay, so the splitting activation thing, again, not 100% sure what they're talking about here. What? And then the next section is the third one? Okay, okay, so the splitting activation, you get the exact same model. This is just a way of training it more efficiently. The reversible layers one does not change the model significantly, and the approximate attention does, and it looks like requires some additional hyperparameter tuning. But, you know, taking quadratic time and memory to, or square root time and memory to train a model, that is a performance trade-off I'd be willing to make, personally. Because you think, like, so imagine, like, GPT-3, $12 million of compute. This is square root of 12. Like, 3 something? Or 12. Yeah, 3.46. So if you had applied that transformation, even if you might have gotten slightly different results, you would have saved $9 million, which I think is like a fairly, I don't have $9 million, but I would sure like to not spend that amount of money. Chirag says, maybe the depth means width. We can cat output from all the heads before passing through feed forward, so that is why feed forward has larger width. Oh, yes, that would make sense. So taking all of the, like, the attention square, and then you take bits off and put it to the side so it's really long instead. Yeah, that would make sense. Let's see if that's what they say. We experiment on a synthetic task, a text task in Wik 8, English Wiki 8, with sequences of length 64, and an image generation task, ImageNet 64 generation, with sequences of length 12K. In both cases, that's 3 cases. In both cases, we show that Reformer matches the results obtained with full transformer, but runs much faster, especially on the text task, and with order of magnitude better memory efficiency. I like the sound of that. All right, let's talk about this locality sensitive hashing attention, which is the one that does change the training dynamics, and it's this one. So they're talking about the third one first. All right, dot product attention. The standard attention used in the transformer is the scaled dot product attention, Vaswani et al. 2017. The input consists of queries and keys of dimension dk and values of dimension dv. This is something that threw me for a full-on loop when I was learning about transformers. The queries, the keys, and the values are all learned values. You do not provide the queries and keys. The dot products of the query with all keys are computed, scaled by square root of dk, and a softmax function is applied to obtain the weights of the values. So I mentioned you have this, like, you know, attention square. This is how you get what the value of each of the points in that square is. In practice, the attention function on a set of queries is computed simultaneously. This is why you get the benefit that you don't get with RNNs, that it's harder to, that you can train it more quickly if you can parallelize it, packed together in a matrix Q. Assuming the keys and values are also packed together in matrices K and V, the matrix of outputs is defined as attention QKV, softmax QK transpose divided by the square root of DKV. Yep. I don't know what else to say about that. Multi-head attention. In the transformer, instead of performing a single attention function with d-model dimensional keys, values, and queries, one linearly projects the queries, keys, and values. I'm really enjoying this paper so far, but if you refer to 3 things in one order, you do not change the order the next time that you refer to them. You keep the same order throughout, or else you confuse your reader. So the thing where, like, the 3 bullet points are being referred to in a separate order in the text and are coming up as different headings, and then these 3 things are being referred to in a separate order here and here. I don't know. It's just a writing nitpick. One linearly projects the queries, keys, and values H times with different learned linear projections to DK, DK, one of those must be Q, DK, DQ, and DV dimensions, respectively. Unless K is squared? Attention is applied to each of these projected versions of queries, keys, and values now. Okay, it's definitely supposed to be Q. In parallel, yielding DV dimensional output values. These are concatenated and once again projected, resulting in the final values. This mechanism is known as multi-head attention. So basically what they're saying here is that, like, the set square is being stacked on top of each other. You can almost think about it like the sort of like combs in a beehive, that they're sort of like all, if you were, I don't know, things don't really move through combs, bees do, but that sort of like stacked parallel structure, where each comb would be an attention head, if that makes sense. I don't think the beehives is actually a great metaphor, and also maybe not very accessible. I don't know how common. I'm trying to think what I know about beekeeping outside of the US, and I know that in some places they use baskets that do not have combs, so I'm just going to stop using the metaphor. Hello near this says hexy shaped. Yeah, they're, okay, no, this is a bad metaphor. They are squares. Or cubes, more accurately. Query value key dimensional cubes. Alright, memory efficient attention. To calculate, so as you, basically what I'm saying here is that you have, for each of these weights, you've got 3 things, and then you have multiple copies of them that are all different. Each of the copies is different. So it's not a copy, multiple versions of them that are all different. That's a lot of values to store. So transformers have a lot of parameters. Memory efficient attention. To calculate the memory use of the attention mechanism, let us focus on the attention computation from equation 1. This one. The 1 is over here. Let us assume that Q, K, and V all have the size, shape, batch size, length, D model. So the length is the length of the input dimension. The batch size is how many sort of samples you feed through at a time. And then the dimension of the model, I think, is just something that you pick as a parameter. That's like how big the model is. The main issue is the term QKT transpose, which has the size, batch, shape, length. Oh, okay. So this DV is not a typo. It is supposed to be DK key value. Okay, so then this is the length of the input sequence, and the number of things that you're looking at. In the experimental section, we train a model on sequences of length 64K. In this case, even a batch size of 1, this is a 64K by 64K matrix, in which in 32-bit floats would take 16 gigabytes of memory. So one of the things that they did in Convert is that they do not use floats to store the... So Convert is a transformer model specifically for picking the next turn in a dialogue. And one of the ways that they reduced the size of their model is that they did not use 32-bit floats. I think they used 16-bit floats? I don't remember. We read the paper a while ago. Which takes 16 gigabytes of memory. This is impractical. And it's hindered the use of the transformer for long sequences. So basically, as you increase the sequence length, you quadratically, or to the power of 2, increase the memory requirements of your model. But you want a long sequence because the benefit of transformers is that you can sort of like look across a sequence and pick out the bits that are most relevant for your specific task. Hello, Douglas. It is important to note that the QKT matrix does not need to be fully materialized in memory. The attention can indeed be computed for every query QI separately. Only calculating softmax QIKT square root of DKV once in memory and then recomputing it on the backwards pass when needed for gradients. This way of computing attention may be less efficient, but it only uses memory proportional to length. We use this memory-efficient implementation of attention to run the full attention baselines presented in the experimental section. Okay, so what they're saying is we aren't storing this matrix. We compute it every time we need it. So we're reducing the memory costs, but I would expect this to increase the compute costs because you're repeating the same computation, I think is the word that I was looking for. You're repeating the same computation every time you do backprop to upgrade your activations. Interesting. But the memory benefit of that is that you don't need to store these enormous matrices, and a lot of them too, because that's the way the transformers work. Okay. Where do QK and V come from? Oh, it's behind my head. The multi-head attention described above operates on keys, queries, and values, but usually we are only given a single tensor of activations A of the shape batch size length D model, e.g., coming from embedding the tokens in a sentence into vectors. Okay, so what they're saying is, I want coffee. That's not what they're saying, that's what I'm saying. Douglas says, what are recommended books, your preference to learn AI from scratch? If you're talking about specifically neural network architectures, Francois Cholet has some, I think he has one in R and one in Python that are pretty good walkthroughs. If you're looking for more of a course, the Fast AI course is very good. That's by Rachael Thomas, who I am a different person than, and Jeremy Howard. I get confused for Rachael Thomas kind of a lot, which is surprising to me because we look nothing alike. But I'll take it. She's a very good researcher and teacher, so I take it as a compliment. Okay, so what they're saying is, so you don't get the queries, values, and keys. What you get at each stage, once all these computations have been done, is just this cube, basically. It may or may not be a cube, is this three-dimensional block where each smaller sub-block contains the activations that have been computed from the queries, values, and keys. So, e.g., coming from embedding the tokens into a sentence of vectors. Embedding the tokens into a second. So, tokens are usually words. And generally word embeddings are vectors. So they said that you're embedding each of these in a... I don't 100% understand that sentence. Havu, sorry if I'm saying that wrong, says, is deep learning really better than some rule-based methods? It depends. So the benefit of a lot of deep learning approaches is that they are more flexible. They are sort of more generalizable so that you can use a more similar system across a wider variety of problems than you would for a rule-based system. The big trade-off there, one of the big trade-offs, is that you are taking time away from developing rules to curating data and doing evaluation. Also, they can be slower because there's a lot. If you're just doing like one operation that's checking whether or not something is like above 3, say in some sort of decision tree, that's going to be faster than, running a whole neural network or running data through a whole neural network. Yeah, if that makes sense. It depends. Like sometimes you want to use rule-based systems. Pushkar says, if they're not calculating the entire matrix for multi-head, how are they calculating the loss for the entire batch needed for backpropagation? Yeah. Well, I'm assuming they're going to get the loss at like the last layer, and then to go back through and do backpropagation, they recalculate the, it looks like they're going to recalculate the activations at each layer and then change them. That's what they're talking about here. To build K, Q, and V from A, so this is the A as the activations, cube, and you want to rebuild Q, K, and V from it. The transformer uses 3 different linear layers projecting A into Q, K, and V with different parameters. Okay, so they're doing like a... For models with LSH attention, we want queries and keys, Q and K, to be identical. This is easily achieved using the same layer to go from A to Q and K and a separate one for V. We call a model that behaves like this a shared QK transformer. It turns out that sharing Q and K does not affect the performance of the transformer, even if we additionally normalize the length of keys K as shown in experimental section 5. Okay, so first of all, what is LSH? Locally shared hashing, I think. So what they're saying is we have A, we want to get Q, K, and V from it. So what we're doing is we're assuming that Q and K are the same, and we are figuring out Q, K, and then a separate V by using a linear layer projection. Is that what this is? Figure 1? What does figure 1 refer to? Excuse me. Okay, so they are going to go into more depth about the projections. Hashing attention. For the locally shared hashing attention, which they did not define before they started using the acronym, we started using two tensors, Q equals K and V, of shape, batch size, length, D dimension of model. We keep the multi-head mechanism intact and focus on the attention computation from equation 1. Trunk says, output of each layer in a transformer is logically the same as an embedding words in each sentence over the entire batch. Batch times length times embeddings. Okay, that makes sense. Yeah, because then, okay. Yes, because the final... So this would be for the encoder, specifically? No, or the intermediate stages of the... No, yeah, that would be for the encoder, specifically. So the first part that takes words in and gives you sort of a numeric representation out. Drop says locality sensitive hashing? Yeah, I think so. Hopefully that's what I said. And then Gruff said, Huba says, when I build a chatbot on Rasa, I have really small data, so can I use deep learning? It depends on the pipeline that you are using. So Rasa uses deep learning in sort of the framework that allows you to build your assistant. So if you're using English, for example, there are pre-trained models that we use that were trained using deep learning, and then you take your additional data, which is smaller, and use it to modify those models so that they're better for your particular task. So it's sort of transfer learning, really. So you don't need to provide enough data to train like a big deep learning model from scratch, unless you don't have... You're working in a language, basically, that there aren't pre-trained models for. You need to do the model pre-training and sort of develop the pipeline yourself. If that makes sense? Hopefully that makes sense. Okay, so let's talk a little bit more about this. All right. So they are focusing, on the attention computation from equation 1. Hello, Detox Mango. As already mentioned, the main issue is that the term KQT, which has the shape batch size length. But note that we are actually only interested in softmax KQT. Okay, so if we look back at this attention, which is the equation, attention equation, they're saying that this the big one right here, this KQT. But we are actually, you could sort of like adjust this. So we're taking the softmax of KQT and then dividing by the softmax, the square root of DK. No, you know. Okay, so DK is the dimension of the keys, which you would already know. So you're only really interested in the output of this part, you don't necessarily have to compute just this separately and save it. Detox Miko says, are you a machine learning developer? I mean, my job title is developer advocate, so I work a little bit more on education, but I would say yes. I'm a developer and I work with machine learning, so yes, broadly. Okay, so they're saying that we're only really interested in the softmax. Where did it say that? Since softmax is dominated by the largest elements, for each query, QI, we only need to focus on the keys K that are closest to QI. For example, if K is a blank 64K, for each QI, we could only consider a small subset of, say, the 32 or 64 closest keys. This is much more efficient, but how can we find the nearest neighbors among the keys? Okay, so softmax finds the, given, probability assigned to a bunch of things, the thing with the highest probability. So they're looking for, so softmax is what assigns probability. Right? Oh, I'm getting that backwards. Rachel, have you forgotten what softmax is? Hush. Blah, blah, blah. Mathematics softmax, not known as soft argmax, normalized exponential function, is a vector that takes as an input a vector z of k real numbers and normalizes them into a probability distribution. Okay, so it's the second thing I said, which is that you take in sort of counts and assign them to a probability. And because probabilities are between 0 and 1, things with high counts are going to be high. Detox Max Mango says it's an activation function. Yes. Yes. And Ragov says, are they approximating computing the heavy softmax QKT using LSH? Looking for things that will yield highest dot because large values influence softmax the most. Yes. That sounds right, Tirag. Yes, I think they are approximating it using the biggest counts or the most related keys. How do they find it? Locality sensitive hashing. The probability of finding nearest neighbors quickly in a high dimensional spaces can be solved using locality sensitive hashing. Okay, interesting. So I guess they mean closest here in terms of probability and not closest in the matrix, because that wouldn't make sense, right? Rob says, would that not compromise model predictive power? Yeah, they do suggest that this method in particular does change the model output in a way that the other two ones that they talk about do not, and requires a little bit of fine tuning. Truck says cosine distance. Oh, that makes sense. So the closest using cosine distance. Okay. Probability of finding nearest neighbors quickly in high dimensional spaces. A hashing scheme that assigns each vector x to a hash h of x is called locality sensitive if nearby vectors get the same hash with high probability and distant ones do not. Okay, and then this distance is, again, cosine similarity. In our case, we actually only require that nearby vectors get the same hash with high probability and that hash buckets are of similar size with high probability. Okay, so they don't care about distant ones not getting a close hash. Okay. We achieve this by employing random projections as follows. See figure 1. To get B hashes, we first fix a random matrix R of size dk dB divided by 2. Batch. Oh, that must be half of the batch size by the dimension of the keys. We then define h of x, which is the hash, argmax, between, out of a set of things, between the random matrix and its inverse, I think. Ooh, if anyone knows what this means, please chime in the chat. Where, oh, I see. Okay, so they're concatenating a random matrix and a negative random matrix, an inverse? No, transpose would be T. Dxminko says, I'm a noob in this area. I've been going through Python programming net, and I'm wondering if there's enough to find work in this area. I'm not a classical statistician yet. I would say machine learning and statistics have diverged a little bit, so I don't think you necessarily need to be a full-on statistician to work in machine learning these days. I will say it is a very competitive field right now, and whether or not you're sort of like self-directed education is going to be enough to get a job is just going to depend on a lot of factors, like your professional background, the sort of projects that you've done, like networking, how you find out about job openings. And things have just changed so much since the beginning of the year that I feel like any job hunting advice I can give is not going to be based on experience that is relevant enough to be helpful. So, good luck. I'm not saying this to be mean. I'm just like, things are changing very quickly in the field, like even in terms of like who's hiring, what they're hiring people to do. So I can't give you a more concrete answer like I could have maybe like a year and a half ago. All right, so, and it looks like no one's chimed in to tell me what the negative means. I'm gonna see if I can look it up. What does a long dash mean in linear algebra? None of these are helpful. Oh wait, algebra symbols list. Let's see if any of these are helpful. Pull this up. So it's just a list of linear algebra symbols. Okay, so it's probably not inverse, because inverse would be raising it to the negative first. What does it mean when you negate a vector? Is it just like element-wise negation? Is everything in it negative? Well, that didn't answer my question at all. Emike says, vector in the opposite direction? Does that mean? I'm just going to look up the word that you typed. Vector in opposite site. Site. What does that mean for a vector? Vectors. Oh, wow. This is all just like vector graphic stuff. C++ reference. Not helpful. Okay. What I think you're saying, opposite direction. Okay. People are timing it. Yeah, what I think you're saying is that like vector A, blah, 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 Z, and then concatenating it to vector Z, blah, 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 A. Correct me if I'm wrong. This method is known as LSH scheme, Adoni et al. 2015, and is easy to implement and apply to a batch of vectors. Amon, any tips for people starting out in NLP after a basic machine learning course? The Jarofsky and Martin text is the sort of like standard textbook people use. Speech and language processing, and it is available on the internet for free. So that's a good book to go through if you're looking for a specific book. And Douglas says, what's your thought about GPT-3? Do you think some jobs in the IT field could be lost or replaced by GPT? I think it is possible that someone might try it. I don't think it will end well for the person that tries it, is my thoughts on the matter. Okay. Okay, easy to implement. That's good. And then I believe we referred to figure 1 in here somewhere. Yeah, okay, so we're employing a random projection. Figure 1, an angular locality sensitive hash uses random rotations of spherically projected points, to establish buckets by an argmax over signed axes projections. That was a bunch of words. All right. Angular locality sensitive hash is a thing where things that are closer together have more similar hashes. Angular means I'm presuming that we're working off of angles. Random rotations of spherically projected points to establish buckets by an argmax over signed axes projections. So you're rotating a sphere. So you project the point to the sphere, then you rotate it, and then you establish buckets by an argmax over signed axes projections. I see. So each of these triangles here is a different bucket. Gotcha. So in this one, the white point is in bucket 0, and the red point is in bucket 3. Here, they're both in bucket 2. Here, the white point is in bucket 0, and the blue point is in bucket 1. Okay, so you've got a sphere. You look at the cosine distance between the 2 points you're hashing. You project them onto the sphere, and you just spin that like Wheel of Fortune, and then you've divided the space into quadrants, and whatever quadrant it rests in, it may not be quadrant, so maybe more than that, that's the hash it gets. So 2 points that are closer to each other are going to be assigned to the same hash bucket more often. I'm picking up what they're putting down. It's making sense to me. I'm gonna put my glasses back on. I don't know why I take them off when I'm confused, but I do. In the simplified 2D depiction, 2 points, sphere. Oh, okay, and this is a circle, so it's a sphere, and you just outside the Richmond Science Museum, there's like a big granite sphere that has the moon on it, and it's a fountain, so it's like on like a little bed of water, and you can spin it and like look at all the different parts of the moon. So just giving that a big old spin, random direction, you got your points on it, and then you take the space around it and use that to assign them to different buckets. I'm getting it. Okay. In the highly simplified 2D depiction, 2 points X and Y are unlikely to share the same hash buckets if they're really far apart for 3 different angular hashes unless their spherical projections are close to one another. Gotcha. This is a very helpful diagram. I get it. All right. Alan says, what a sentence. Yeah, it took me a second. And Shrunk says, opposite would mean that the angle between x and negative x is pi. That sounds like some trigonometry I have not dusted off in a while. All right. Easy to implement to apply to a batch of vectors. Yeah, now that I understand it, I would agree. That does seem fairly easy to implement. That actually seems like it would be a pretty good, intro graduate level course assignment. Knowing our LSH scheme and the general idea of hashing attention, we will now formalize the LSH attention we use in this paper. We first rewrite the equation for normal attention, 1 for a single query in position I at a time. So, for O of I, which is attention, I guess? Where did O come from? I think they're just giving that I think they're just using that to refer to the rest of the equation, but I want to have something to call it. Okay, so I think O is just going to be LSH attention. And then your summing over J is just an index, I think. P of I, where J from, what's the curly brackets? One sec. Let me pull up my symbol list. Blah, blah, blah. Set. Okay, so this is a set. Is in a set from J to I greater than or equal to J. Okay, so that's the query position. So I'm guessing it starts at like 1, maybe? Hello, Denalish. Enrique says 180 degrees is pi. I vaguely remember that. Avinash says, I love the reading group. Are there any other reading groups for papers in CV and ML? Ooh. Not that I know of off the top of my head. If anyone does, please feel free to chuck them in the chat. I will admit that I sort of only very tangentially pay attention to computer vision, and kind of when it's mostly I hear about the bad applications. All right. Okay, so we're taking the dot product of query I and key I minus Z. Where did Z come from? Did we talk about Z beforehand? I don't think we did. All right, wherever Z came from. Maybe this is a function. P of I, and then the values. Except that the queries and the keys are identical for this particular approach, is I believe what they said. We introduced the notation PI to represent the set that the query in position I attends to. Okay. Oh, they define them underneath it. I was scrolling back up looking for stuff. Okay, so these are a set in your a point in your input sequence. Everything else that it attends to is P of I. And then Z to denote the partition function, i.e. the normalizing term in the softmax. Okay, so this is part of the softmax. For clarity, we also omit scaling by the square root of dk. So this is what they are using to replace the matrix, these matrices that are combined. Multiplication. Wow. Matrix multiplication is what I'm trying to say there. So they're replacing that with, at a single point, single query position I, taking the query and key, and then taking the dot product of the query and key, and then subtracting some sort of normalizing factor like you get in softmax. For clarity, blah, blah, blah. For batching purposes, we typically perform attention over a larger set, P wavy hat. Oh, I used to know how that said. P, woo, toupee. Rudolph says the activation function is Z, question mark. No, I don't think so. I think that is the part of softmax. The normalizing is the thing that makes it all add to 1 because it's a probability. Yeah, so that's the bit that makes it not 12, I think. Could be wrong about that, but I think that's what that is. All right, and we do it over a larger set, p tilde, I think, 0 through the length. Okay, so you pick your pi out of your points that point to an index that's somewhere in the length of your sequence, while masking out elements not in pi. So you go over your sequence and you just ignore the ones where there isn't any attention. Pretty much the same thing. So this M here is, okay, so this is the masking. So if you are at a point and that point does not pay attention to another point, you just chuck that out entirely, which makes sense because there's a train transformers tend to be extremely sparse. There's a lot of zeros. This is just sort of like ignoring them bits. All right. Now we turn to LSH attention, because this is just what they're doing. Instead of storing those enormous matrices, they're performing sort of like element-wise computation on the fly when it's needed for backpropagation. Scroll. Now we turn to LSH attention, which we can think of in terms of restricting the set pi of target items and query position I can attend to by only allowing attention within a single hash bucket. Oh, okay. So they do their sphere rotation, and then if the 2 points are not in the same hash bucket, they add that to the points that's being masked. So they just chuck them out entirely. Okay, that makes sense. Figure 2AB shows a schematic comparison of full attention with a hashed variant. Part A depicts that the attention matrix for full attention is typically sparse, but that a computation does not take advantage of this sparsity. So you're updating a lot of zeros. In B, the queries and keys have been sorted according to their hash bucket. Since similar items fall in the same bucket with high probability, but it is probabilistic, so not always, because two things could be real close to each other and just like, boop, right on the sort of dividing line between two buckets. The full attention pattern can be approximated by only allowing attention within each bucket. Yeah, okay. I'm getting it. It's making sense to me. Simplified depiction of LSH, locality sensitive hashing, attention showing the hash bucket sorting and chunking steps and resulting causal attentions. A through D, attention matrices for the varieties of attention. Okay, so A is all of these cells, I guess, are being computed, but only some of them actually have attention in them. But even though it's very sparse, there's a lot of zeros, you still have to go back and update and store all the zeros, which is slow. And then when you bucket, so you only look at things that are close to each other in cosine distance after your random rotation, now you only need to pay attention to things inside the buckets. So you have this, each item only pays attention to other things within the same bucket, which is how you get away with computing things item-wise every time you backpropagate, because you don't need to do it for every single attention bit. You can ignore most of the cells, which are also the cells that are mostly empty. So you got your queries, you do your bucketing, so things that are closer to each other pay attention to each other, and then you chunk them, so you can use your GPU or TPU, whatever you're using, and then you attend within the same bucket. Oh, I see. And okay, so these are all the same bucket. So yes, and previous chunk. Attend within same bucket and previous chunk. Oh, I see what they say here. So what they're saying is that sometimes the bucket is going to spill over into a different chunk, and when that happens, chunk 0 does not pay attention to chunk 1, but anything in chunk 1 that's in the same bucket as chunk 0 does pay attention. So these arrows all go backwards. Okay. And then we haven't talked about C and D yet, which I'm assuming he's going to say the same thing, but like all that chunk stuff. Raghav says, are we losing the ordering of the tokens in the sequence with LSH-based sorting? That's a really good point. So in the intermediate layers of a transformer, order doesn't matter. So yes, you are losing the sort of like the queries and the keys being sorted in the same order, but that is not necessary for the performance of the transformer. The way that you get order out is that there is another term, I forget what they call it in the paper. I think it starts with a P. And they had like, in the original Swanee paper, it was like way confusing, but basically you just have like a thing that you remember that's like, this point came from 1, this point came from 2, or however it is that you're assigning order, and then you do that at the very end. So that information is not important in the middle layers and gets sort of like added at the end, if that makes sense. So you lose that, but only in the way that the matrices are visually shown. If that makes sense? I can say, does that make sense, quite a bit more, and see if that helps. Yeah. Oh, what was it called? I'm just gonna pull up the Swanee real quick. Swanee 2017. The NERIPS proceedings, the PDF. There we go. All right, so oh, did they leave it out of the? Is it only in the archive paper? Or am I hallucinating it? I don't think I'm hallucinating it. Oh, it might have been a BERT. Let's see. So this is the published version from NERIPS, and then this is the archive version. Oh, maybe it wasn't BERT. Okay, so here's the they used a sinusoidal embedding to provide the mapping from the place it was at the beginning to the place you want it to be at the end. I thought there was a visualization in here that maybe I am just showing the sinusoidal embedding. I thought it was green. It might have been in like one of Jay Alamer's posts or something that I'm just making up. But blah blah blah. Okay. Truck says, aren't the residual connections meant to propagate the position information? That could be the case. That's not my understanding, though. I could be wrong about that. Please feel free to share resources you have that are relevant. And if it does, presumably that's something that they're going to talk about. Blah, 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 blah. Where were we? Okay, we were talking about this. Hash buckets in this formulation tend to be uneven in size, which make it difficult to batch across buckets. Moreover, the number of queries and the number of keys within a bucket may be unequal. In fact, it is possible for a bucket to contain many queries but no keys. That's right, because we're treating queries and keys as the same for this. To alleviate these issues, we first ensure that HKJ and HQJ equals HQJ. What's H? The hash? I guess. By setting KJ equals to QI over, just gonna quickly check. This is a little cheat sheet. Is it in here? Norm. Okay. QI divided by the norm of QI, normalized. Next, we sort the queries by bucket number and within each bucket by sequence position. This defines a permutation where I, special arrow S, after sorting. Okay. In the sorted attention matrix, pairs from the same bucket will cluster near the diagonal as depicted in figure 2C. We can follow a batching approach where chunks of n consecutive queries after sorting attend to each other and one chunk back, figure D. Okay, 2D, so that's what we talked about earlier. Following our earlier notation, this corresponds to setting P toupee to P wavy hat, J. Okay. SI divided by M lower bound minus 1 is less than the lower bound of SJ divided by M is greater than the lower bound of SI divided by N. So I think these two are talking about where the boundary is. This is talking about the sort of the order of attention and that it is going backwards. Okay. So, I see here. So the points here are the queries and the keys, and we want to make sure they're relatively evenly distributed, I think. If max P of I is less than M, then P of I is, I'm gonna look at this again. Does this have set theory notation? I don't think it do. No, it don't. Subset? Pi is a subset of P hat I? No, P hat I is a subset of Pi? Oh, something. In practice, we set n equals 2L divided by the number of buckets, where L is the sequence length. The average bucket size is L divided by the number of buckets. And we assume the probability of a bucket growing to twice that size is sufficiently low. That's right, because again, this is assignment to buckets is stochastic. The overall process of LSH attention is summarized in figure 2. Okay. Raghav says proper subset. Thank you. I should just have like a cheat sheet on my wall. Yeah, I think people would think that I'd memorized all of the set notation. I had at one point, let me put it that way, I'd memorized it in spring quarter of 2015 when I was taking formal semantics. If you'd asked me that quarter, wow, I would have been fast on the draw. Just at the moment, however, not quite so much. PI is a set of PI toupee. Because it's not a hat, it's wavy. Anyway, hats can be wavy. I am losing the plot a little bit, and it is 10:17 at my point, so I think I'm going to wrap it up here, and we will return with multi-round LSH attention, not next Thursday. I'm going to be out next Thursday and Friday. I'll post on YouTube about it. But the Thursday after that. And I may or may not have a math buddy with me on the stream to help me with symbols and just sort of talking through the math. All right, so far we are on page 4 of, how many pages is this? I guess ICLR allows much longer papers, and it is a long paper. 4 of 9 pages. So hopefully we'll finish it next time. The experiments will probably be pretty quick to read through. I hate this. I hate the related work at the end. The related work should be at the beginning. This is my strong personal aesthetic opinion as a former researcher, I guess. A trained consumer of research literature. Yeah, so next time we're going to talk about reversible transformers. We're going to talk about the analysis of a synthetic task. When are they going to talk about the splitting the activations inside feed-forward layers? Because this seems like something that you could implement right now in any transformer, or honestly any feed-forward architecture, and just save yourself some time in compute, because it doesn't change the model. So I'm really interested in learning about this point, but the order that things are arranged in this paper seems to be chaotic, and I don't know when it's going to come up, but next time. Raghav says, we should create a Rasa math buddy. That could be fun. I'll just sort of describe what a symbol looks like to me in human words and see if it can get it. You need a very specialized data set for that. it might, it feels like something that would it exist? Who would need that? Math students. Who would create that data set? Math pedagogy people. People who teach higher math are, in my experience, not very committed to math pedagogy. So, yeah, may or may not exist. All right. Thank you so much for joining me. I hope you found this helpful, interesting. Definitely, I think I've learned some things. I'd never heard of locality sensitive hashing before, and it's really cool. I think that's definitely something I'm going to remember from, I mean, they did not propose it in this paper. This is a method that's been around, but I'm learning about it for the first time now. So definitely something that I'm learning from this paper reading. All right, so I will be back tomorrow with more live coding. Also, if you were here yesterday for the live coding, I did figure out that I should instantiate my class. So I did do that, and hopefully we're just going to try it and it works. And oh god, hopefully next week we're going to be able to move our assistant to Rasa X so everybody can talk to it. It's going to be great. All right, wrapping it up here. I hope you all have a really great day, and I will be back tomorrow morning. I'll talk to you then. Bye.